We're going to wrap up this unit on algebraic vectors by taking a look to see just how powerful vectors really are, not just in theory in the real world. We're going to put together what we've learned about the dot product and the cross product and 3D vectors to take a look at the key things or the key takeaways, the key tools that we've got from this dot and cross product. So the dot product tells us how much one vector points in the direction of another, a way to measure alignment, angles, and work. Remember, we talked about it in terms of work, where we have one force acting in the direction of displacement, and we want to know how much of that force is causing the displacement in that direction. Then we had the cross product, which gives us a new vector. It has direction, and that vector is actually perpendicular to two other vectors. And this helps us measure rotation. It can help us measure area, and it can give us direction in space. But today, we're going to stop seeing these as just questions for questions and start using them as applications. So we're going to talk real world today. Have you ever wondered how engines transfer force through rotating parts? Cross product. Want to calculate how much work is done when you push something at an angle? That's the dot product. When you're trying to find the area of a triangle or a parallelogram in 3D space, that's the cross product. And we're going to look at torque and finding the area of 3D shape today specifically. So, and we're also going to try and remember that if two vectors are perpendicular or parallel, then we can use either the cross product or the dot product to help us figure that out. Now, these aren't just calculations. They're actually how engineers build bridges, how animators make 3D models come to life, and how physicists predict the motion of the world around us. So our goal today is to learn how to take these mathematical tools, the dot product and the cross product, and apply them to solve problems. We're going to analyze motion slightly in the world of torque and model some real world situations. So let's get started by looking at an example and to think about something we may already know. Okay, so just as a reminder, work performed is the product of the magnitude of the displacement traveled by an object and the magnitude of the force applied in the direction of that motion. And we can use dot product to find this. And remember, the units are in Newton meters, but that is also joules. And this really is dot product when we've got the magnitude of one vector projected onto the magnitude of another vector. In this case, what we actually have is the work being done is our force vector times the projection, our displacement vector times the projection of our force vector on that displacement vector. So let's look at an example and just hold on to that and see if we can figure this out. So we know that work is the product of two things, the magnitude of displacement and the magnitude of force that's applied in the direction of that displacement. We've already talked about the fact that this is the magnitude of the projection of the force onto the displacement, and that is the dot product. So we can take either the displacement and dot it with the force, or we can dot the force with the displacement. It doesn't matter. Order does not matter in the dot product. So let's take a look at a question and let's see if we can come up with an answer. So a force with units in newtons is defined by this force vector in 3 space. So we have an x, y, and a z component. We're no longer in 2 dimensions. We are now in 3. And the force is equal to 300, 700, 500. And this acts on an object with a displacement in meters, represented by this displacement vector is represented by 3, 1, and 12. So we're being asked to determine the work done in the direction of travel. So let's just think about what this looks like for a second, and I'm going to do my best to draw it out here. So here's my x, x, y, and here's my z. And I have my force vector, which is significantly stronger than the displacement, or has more magnitude than the displacement. So I will have a force vector acting somewhat in that direction. And then over here, I have my displacement vector. So if we want to think about what's happening here, what we have is we have this projection, the amount that the force is going to project onto this displacement. So we really are looking at the projection. So that's what we're looking at. This highlighted bit here would be the projection of the force onto that displacement. So we can do that though using the dot product. We don't need to worry about the projection part of it. So we know that work is equal to the force dot the displacement. Now remember, the dot product tells me that I'm taking my x values multiplied together plus my y values multiplied together plus my z values multiplied together to get a new scalar value, to find out what the actual amount of work being done is. So we have 300 times 3 plus 700 times 1 plus 500 times 12. And really, if we want to think about this, it's 300 newtons in the x direction, 700 newtons in the y direction, and 500 newtons in the z direction, if we wanted to think about it that way. So we end up with 900 plus 700, I hit a button, plus 6,000. And that gives us 7,600 Newton meters, or remember, we can say that that is joules. Work can be measured in joules. Now, I happen to think the next part of this question is a little bit more of the interesting part, because this is something we haven't thought about before. So, determine the work done against gravity. So, we know, or maybe we remember, that gravity is going to act straight down in the negative z direction. So if it's going against gravity and gravity is acting in the negative z direction, then the opposite of that is going to be the amount of gravity that's acting in the positive z direction. So we're only going to use the z direction and the force. So using our same idea that work is equal to the force crossed with the displacement, but remembering that we're only really worrying about this z component of the force as it's affecting the rest of it. So really what that means is we're going to say that the amount in the x and the y is 0. So we would have 300 times 0 plus 700 times 0, because our x and our y directions are 0. We don't have any displacement in this case in the x and y direction when it comes to gravity. But what we do have is 500 newtons of force acting in the z direction, which the displacement in the z direction was 12 units. This is 0, this is 0. So we are left with 6,000 joules of work being done in the z direction of this vector, opposite to gravity. So the amount of displacement, the amount of force that's needed to counteract this amount of gravity that's trying to pull it down is 600 joules. 600 joules of work is what's being done to counteract gravity. Okay, so we've just seen that we can use the dot product to determine work. Now let's take a look at the cross product. And we can actually use the cross product to determine the area of a parallelogram. So just as a reminder, the area of a parallelogram is equal to the base times the height. So the base here in this case is vector v. Don't know why it's down there. And we have one side of our parallelogram is vector v, the other side of our parallelogram is vector u. If we complete the parallelogram, then we have v on the bottom, u coming up the side. Now, if we think about this, so the area of this is the base times the height. Well, this height in this case, if we know this angle theta, we can figure out the height using our basic trig, because I know then that sine of that angle is equal to the height, or my opposite side, divided by my magnitude of vector u, which happens to be the hypotenuse. Well, rearranged to solve, so then the height is then equal to the magnitude of vector u times sine of that angle. Let's put it all back together. And the area for this geometric vector question would be the magnitude of vector v times the magnitude of vector u times sine of the angle. Now, we're not too worried about what's happening direction-wise at this point. This is just going to be the magnitude or the area. So we don't really have a direction, it's a plane. So this is our geometric formula of the cross product. The magnitude of vector v times the magnitude of vector u times the angle between the vectors. Now, the algebraic form of the cross product can be used to find the area of a parallelogram in 3 space, or in 3 dimensions, and that's what we're going to take a look at next. So here is our question. We are given 3 points of a parallelogram. We're given point P is at 7, 2, -5, Q is at 9, -1, -6, R is at 7, 3, 3. Those are 3 of the points. We are missing one of the points, and that's actually going to be our first job, is to figure that out. So let's draw it just so we know what we're looking at. So we have a regular old parallelogram, hopefully a little more parallelogrammy than what I've just drawn. And we have the points at P, Q, R, and S. We know P is 7, 2, 5. 7, 2, -5. We know Q is 9, -1, -6. We know R is 7, 3, 3. We don't know S, but we do know it will have an X, Y, and a Z component because it's in 3 space. So that's what we're going to be trying to figure out. So to determine this missing point, we need to remember what we know about parallelograms. So if I have a parallelogram, all things being equal, then PQ, the line PQ or the vector PQ, will have to be equal in length or in magnitude to the vector that's represented by this over here, SR. So these two will be equal to each other, and that makes sense. If it's a parallelogram, that's what it's going to have to be. So we can do some math to figure out the length of each line segment and then work backwards. So we're going to figure out the length of the side line segment PQ first of all. So remember, I can take my x2 minus my x1, my y2 minus my y1, and get my new values. So if we do that, we end up with 9 minus 7 for my x value, -1 minus 2 for my y value, and -6 minus -5 for my z value. So that gives me coordinates, or for the length of PQ for this vector, of 2, -3, -1. So if PQ is equal to 2, -3, -1, and we know that point R is 7, 3, 3, working backwards from what we just did here, then we know that S must be our R value minus whatever the X value is, 3 minus the Y value, and 3 minus the Z value. Well, we happen to know that they are going to be equal to, it's going to be equal to this PQ value. So therefore, we can say that it's 7 minus 2, 3 minus -3 becomes +3, and 3 minus -1 becomes 3 plus 1. So that gives me a point of 5, 6, 4. And I'm going to rewrite that over here just so we have a little bit more room for the rest of it. 5, 6, 4. Okay, so now we know the coordinates for that point. Now we're being asked to determine the area of this parallelogram, PQRS. Well, remember, the area is the magnitude of the cross product. So if we have the area is equal to the magnitude of the cross product between the base and between the two sides. So the area will be the length of this side times the length of our other side, PQ times PS, and we just want the magnitude of it. So this is where we're going to use our cross product. So we have PQ. We already know PQ. We found it over here. Over here. There's PQ. We need to find PS. So that's going to be our first step here, is to figure out what PS is. So PS will be 5 minus 7, 6 minus 2, 4 minus negative 5, which gives me a PS coordinates of -2, 4, and 9. Okay, so now we are going to take the cross product between these two. I wish I had have given myself a little extra space on this piece of paper, but I did not. So remember, when we're doing the cross product, we aren't going to worry about the fact that we haven't memorized any formula. We're going to use our 2 points and just do the cross product. So remember, for PQ, so I'm going to start with PQ, and I'm going to go write them down in a column. So I'm going to do -3, -1, 2, and then repeat my second value. Then I'm going to do the same thing for PS that we just found. 4, 9, -2, back to 4 again. And now I am going to cross these. So my X value will be, I'm going to do it down here. Okay, my X value will be -3 times 9 is -27. Okay, so we get -27 minus 4. We get -1 times 2, which is -1 times -2, which is 2, minus 2 times 9, which is -18. And then we have 2 times 4, which is 8, minus -3 times -2, which is 6. So -6. So that gives me a cross product of -23, -16, and 2. So now we're going to come back up to here, and we're going to put this in here. So that is my cross product. So my cross product is the magnitude of -23, -16, and 2. But I need the magnitude. And remember, to find the magnitude, I'm going to take the square root of the sum of the squares of all the values. So this is going to equal, I can drop the absolute value now because it's going to be positive anyway, because I'm squaring everything. Plus -16 squared plus 2 squared. And that is going to give us the square root of 789. That will be the exact value, but I can write that as an approximate value of 28. If I were to take the square root of 789, it's approximately equal to 28. And that would be 28 units squared. We don't have the units. So now the last part of this question, part C, asks us to determine the area of the triangle that's bordered by PQ, or that has points at PQR. So if I were to draw out our parallelogram again, and here's P, here's Q, here's R, and here's S, well, now really what I'm doing is I'm looking at this triangle here that's PQR. Well, what do I know about the area of that triangle? Well, it's half of the area of the parallelogram. So the area of half of this will be my root 789 simply divided by 2, which gives me an approximate value for the area of 14. And that makes sense. Half of 28 is 14. One of the direct physics applications of this idea of cross product is this idea in physics that we call torque. And torque is a measure of the force acting on an object that causes it to rotate. So think anytime you pull on a door handle that's a lever, anytime you turn a wrench around a bolt of any description, you are causing torque. Now, torque is represented by the Greek letter T, which is the Greek symbol tau, and torque is measured in Newton meters or in joules if you want, but in Newton meters. So to get torque, it is the cross product between the force and the torque arm. So we need to put a little definitions around what this means. So the force is just the force that's applied. If we take a look at this example just down here, we can see that we have a wrench. It is around a bolt, and we have a force being applied. So that's the force that's being applied. The R in this case represents the arm, and that's the radius or the displacement from the axis of rotation. And here is my axis of rotation. So there's my axis of rotation. And the R is the arm length or the radius, and it points from the axis of rotation out to where the force is being applied. Now we will have an angle in between there, and that will be the angle that's in between the two vectors. And because cross product is a vector, it has both magnitude and direction. So that means we need to know, we need to use the right-hand rule to determine the direction of the torque vector, and it will either be into the material. So the force is acting to put, and remember, this is perpendicular, right? So this is a force that's perpendicular to the to those two vectors. That's why this works out so well, because you can imagine we've got a force acting in this plane and a force acting in this plane. It's moving in this direction, and the force itself, the torque, is actually going, in this case, into the page. And we're going to talk about why that is here in a second. But it does have a direction, and it will either be causing a torque into the material, or if we are turning it in the right direction, out of the material to loosen the bolt. Okay, so now that we've got that laid down a little bit, and we're going to use our regular cross product. So we have the radius or arm length times the force times sine of the angle between them, all times this idea of this normal force that's acting perpendicular to the two other forces. So let's take a look at an example. And this is a real life example. This is something that happens every time you use this particular tool. So we're using a wrench to tighten a bolt. A force of 60 newtons is being applied in a clockwise direction. So here's our force of 60 newtons right here, and it's being applied in a clockwise direction. So you can imagine you're pushing down on it or pulling down on it, and it's going to turn in a clockwise direction. And that 60 Newton force is at 80 degrees to the handle. Now, this handle happens to be 20 centimeters long away from our axis of rotation. So we have everything we need to be able to calculate the magnitude of the torque. Remember, magnitude is only the scalar amount. So we're going to start by just calculating the magnitude of this torque. So we know that the magnitude of the torque is equal to the radius of the arm times the force that's being applied times sine of the angle between the forces. Now, remember, when we're doing this, it has to be tail to tail. So we need to move this force vector, and we can do that without changing its angle, and we can move it so that it's tail to tail, and that would move it over here. So now that this force vector with a magnitude of 60 newtons has been moved over here, now we need to see, we need to know this angle here because that's what we're dealing with. Well, you might have noticed that this is the Z pattern, our think way back to grade 9, maybe even before that, to when we're trying to determine angles. And it's that alternating angles are equal. So our angle here will also be 80 degrees. So if you had already gone ahead and done this one and used 80 degrees, I have good news for you. You're going to get the right answer. But if you didn't move it and tried to figure out the direction, that's where you're going to run into problems. Okay, so let's come on back over here now and let's plug in some values. So the magnitude of my radius is 0.2 meters. Remember, it has to be in meters because this is going to be in Newton meters for our units. So I need to have that distance in meters times the force of 60 newtons times sine of the angle, and my angle is 80 degrees. There's no direction here right now. This is simply just the magnitude, and that is 11.82 Newton meters. So now we need to think about in what direction the torque vector will point, and we're going to use our right-hand rule again. So we know that we have, this will be R crossed with the force, and it's always going to be R crossed with the force. So the torque vector will be perpendicular to force and arm vectors, which means it's either coming out of the material, loosening the bolt, or going into the material, tightening the bolt. And this makes sense. So we're going to come back to that part. I'm not going to give that part away yet because some of you might have figured this out already. So we're going to use our right-hand rule. So my right-hand rule says, and I wish you could see my hand right now, but I know you can't. My right-hand rule says that I'm going to place my fingers so that they are pointing in the direction, and I can't draw it all, but I'm putting my fingers so they are pointing in the direction of the vector that's being crossed onto the other one. Then I'm going to curl my fingers in the direction that I'm going. And the only way that I can do that is if my thumb is pointing into the page. So if I'm curling my fingers, I'm going to try and draw this a little better. So if I have my fingers pointing along this direction, so here's top profile of my hand, and I curl my fingers to be pointing in this direction, my thumb will be pointing directly into the page. So this means that my normal perpendicular vector will be downward into the material. Into the material, whatever the bolt is going into. And that means that it's tightening. And the reason that I said I didn't want to give it away too soon, if it's moving in a clockwise direction, I don't know how many of you have heard the expression righty-tighty, lefty-loosey. Well, if it's turning to the right, it is tightening it because the torque vector is going into the page. Now, how would we write this out? Well, we would say that our torque, tau, is equal to 11.82 Newton meters. Now, this is where we have to multiply this by our normal vector, and it's going to be negative of the normal vector. And remember, it has a hat. And I'm going to just put this negative out in front. So it's negative 11.82 Newton meters perpendicular to the two forces that are acting on it. So that's how we would solve this. And this negative just means that it's going into the material, not out of the material. Okay, there are lots of questions here for you to practice. I'm going to give you a work period tomorrow to be able to work on them. The unit assignment will also be posted by tomorrow evening. So go ahead and do the practice questions. If you have any questions, feel free to send me an email.